In Lecture 16, we're going to take a look at typedef, that is, define type names, and we're going to take a more thorough look at const. Now, we've been using one example of a typedef, which is size_t, and we need to describe what that's about. We've also been using const declarations to create things like const objects containing the value of pi, let's say, or pointers to CL node const in the case of our character list code, or a reference to an employee const where we wanted to use passing by reference for efficiency, but we wanted to make sure that the called function didn't change our employee object. So these are the things we're going to take a look at here in Lecture 16. Now, what the word typedef does is to allow you to define a simpler name for some other data type. One particular use of typedef is to define a name for some kind of system or compiler dependent value. Using typedef is fairly straightforward. What you do is to declare a variable that is of the data type that you want to create your own type name for. Then you simply stick the word typedef in front of that variable declaration, and now what used to be a variable name is a data type name. It's an equivalent name for the data type that the variable is declared to have. Let's convert this hand-waving theory to a real example. I have here an object, pi, whose data type is pointer to int. So pi is a variable whose data type is pointer to int. And let's suppose I need to use a whole bunch of pointers to ints in a section of code, and I would like to have a simpler type name that I can use instead of the notation int star. Well, here, if I just look at the part that I've highlighted in yellow, I'm declaring a variable named ptint, whose data type is pointer to int. But merely by putting the word typedef in front, ptint is now a defined type which stands for pointer to int. Consequently, I can use ptint to declare variables. pk here is a ptint. That really means that internally pk is a pointer to int. As I mentioned, we have been using size_t, size_t, when we've been working with things like the lengths of C-style strings, or the lengths of character lists, or the number of nodes in a binary tree. That is, values that cannot be less than 0. Size_t is defined in one of your header files either as the unsigned data type or as the unsigned long data type. It's up to your compiler vendor to decide which of those two type definitions is appropriate for your system and your compiler. As you gain more familiarity with the standard library, you'll discover that there are a bunch of these typedefs, which are defined types whose names end in _t, like size_t. Pointer diff_t and wcar_t and various others are similarly typedefs. And you can use typedefs yourself when you think it's appropriate or helpful. I do want to be clear, though, that a typedef is not a new data type, unlike a class. A typedef is merely a different name for an existing data type. All right, so now we're going to take at more uses of const. As I've said before, we saw two uses of const previously. We've used const to indicate that a, quote, variable, unquote, can't have its value changed. Such an object must be initialized in its declaration. Here we have pi declared as a double, const, and we've provided an initial value for pi. Now, in fact, we've provided more digits of precision that will actually fit into pi, but that's okay. The second use of const is when we want to call a function, and for efficiency, we want to pass a reference to an object, const, indicating that function will not change the referred to object, or similarly indicating that the function will not change a pointed to object. Before the const keyword was introduced, originally in the C programming language, If you wanted to define a constant, you would use a mechanism called pound define, which is another preprocessor directive like pound include. So this notation here says I want to pound define the token pi to be replaced with the token 3.14159 blah 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 blah. And literally what would happen as the preprocessor went through your code, any occurrence of this token pi, capital Pi, would be textually replaced with 3.1415926 blah blah before that textually modified source code would be passed along to the compiler. All right, so a variable had a name and had a data type and optionally was given an initial value. A variable was stored in memory and its value could be changed. A constant, on the other hand, merely identified that a certain token should be replaced with some other sequence of characters. You can still use pound define constants in C++, but people tend not to. Okay, so with the introduction of the const keyword, we now had two different ways of defining constants. We had the pound define mechanism and the const keyword mechanism. So to talk about the difference between these two types of constants, people would talk about pound define constants and const variables. Now, that latter one, a const variable, doesn't really make sense. A variable is variable. What does it mean to say that a variable is const? So the more formal terminology that people eventually settled on was that what we used to just call a variable is now referred to as a symbolic variable, meaning that it has a symbol, pi, associated with a value stored in memory, and that value stored in memory can be modified. A manifest constant, on the other hand, uses the pound define mechanism and simply replaces a token with some other sequence of characters. That's compiled directly into the code and can't be changed. Then a symbolic constant has a symbol associated with a certain value stored in memory. That value has a data type, but that value cannot be changed, even though it is stored in one of the data areas of memory. Okay, and so slide 9 summarizes the distinctions between these terms symbolic and manifest and variable and constant. Okay, so you may or may not recall that when we overloaded the put_to or insert operator for the OStream class as the left-hand operand and a binary tree as the right-hand operand, we passed in a reference to a binary tree object as our right-hand argument, and we then called on that BT object the put_to_OStream function, passing in the OStream parameter OS, and then we returned OS. We returned a reference to an OStream when we were done, enabling us to chain together a sequence of insert operations. So starting with cout, we could insert a binary tree, and then taking the result of that, which was itself a reference to cout, we could insert a new line character, let's say. We are not, within this function, changing the binary tree object, so why didn't we declare that as a reference to a binary tree const? Well, in a nutshell, the reason we didn't do that was because we didn't yet know how to indicate to the compiler that put_to_OStream itself was promising not to modify the binary tree. Here on slide 11, we're showing some similar kinds of examples. An application developer who doesn't and shouldn't know about the internal details of how your binary tree class is implemented can declare anything to be const at any time. So in this main function, in the first 3 lines in black, we're declaring bt1 as a binary tree variable, and we are inserting 6 values into that binary tree object. Then in the red code, we're declaring bt2 as a binary tree const. We're initializing bt2 using our copy constructor as a copy of bt1, and that all works fine because we have said that bt2 is a const, we have initialized bt2 in its declaration, and once it's been initialized, it can never change. So it makes sense that bt2.insert minus 5 should fail. We have declared that bt2 is a const, insert modifies the object, and therefore insert of minus 5 into bt2 should fail. But if we ask what the size of bt2 is, we're also, at this point, going to get an error because the compiler doesn't understand that the size member function is not going to change the binary tree. All right, so why does the compiler not know this, and how can we fix it? Well, in the class definition of our binary tree class, we have to tell the compiler which ones of these functions can be invoked on const objects. And we do this in a kind of an awkward way by sticking the word const onto the end of the declaration of each member function. So here's how that looks. Actually, let me lead my code on slide 11 up. We want size to be able to be invoked on a const binary tree object. And to tell the compiler that that's okay, we stick the word const at the end of the size member function's declaration. Similarly, we do that for the min function, and for the sum function, and for the mean function. And down here, we're also going to do that for the put to ostream function. We're also going to do that for the overloaded equality test function as well. So these consts at the ends of these declarations promise the compiler that these functions will not change the current binary tree object. You could argue that the compiler ought to be able to figure that out by analyzing the code of those functions, but recall that the class definition is typically in a header file, and an application developer using this class will need to be able to compile their application just by including the header. We can't expect the compiler, each time we compile an application, to go out and analyze the internal details of the implementations of these member functions to figure out which ones are legitimately const and which ones are not. So we, as the developer of the class, have to take this responsibility on ourselves and declare as const the member functions that don't change the current object. Notice which functions here on slide 13 are not const member functions. Obviously, the insert member function is not const. It explicitly does change the internal makeup of the binary tree. Likewise, the assignment operator is not const. It certainly changes the internal representation of the current binary tree to become a copy of the other tree that's on the right-hand side of the single equal sign. Now, having declared 6 of these member functions as const within the class definition, we also have to go through and update the individual member function definitions by adding the const keyword at the end of the declaration line in each member function definition. Recall that these member function definitions are typically going to be in a separate code file that we as the class developer will be able to look at and modify, but application developers in all likelihood only have access to a pre-compiled version of this file. Now, if you declare and try to define a member function as const, in this case we're defining the mean function as const, then the only member functions it can use internally are member functions that have also been declared const. But of course the sum has been declared const and the size has been declared const. Neither of those two functions modify the current binary tree object. Returning to our overloaded insert operator, now we can declare the reference to that right-hand binary tree object as const because in the class definition we have declared put to ostream as a const member function. Now, this constness of these various functions has to be percolated all the way down to the lowest levels of your implementation of the binary tree, including all of the helper functions. So if we have specified that the binary tree size member function is const, that means that the size member function is only able to call functions that promise not to change the tree. And since the size member function calls this binary tree size helper function, we will have to ensure that the binary tree size helper function takes a pointer to a BT node const as its parameter type. Fortunately, back when we were implementing these helper functions, we were careful to use this kind of parameter declaration for any function that did not change the underlying values or shape of the tree. That is, the binary tree size helper function has to promise not to change the tree in order for the binary tree class size member function to be able to call the binary tree size helper function. Okay, so you can see with all of this downward percolation that adding constness to a class is not something you want to do after the fact. That is, if you have defined a class and the member functions in that class use various helper functions and so on, and then you come along and decide after the fact which ones of those member functions ought to be const, you're going to have to traverse down through the whole tree of code and make all of the functions that those member functions depend on also promise not to modify the object. It's much better, now that you know about const, to be consistent and careful about using const at every level as you build up your hierarchy of helper functions and member functions. Once we have gone through this process, now our binary tree objects can be const and will behave in the same consistent way that users expect. Here on slide 18, once again, BT2 is a binary tree const initialized from BT1. We cannot insert a value into BT2. We would expect that that should not work, and it won't work because the insert function has not been declared const. We'd expect that we should be able to get the size and the mean from BT2, and those do work because those have been specified as const member functions. We should definitely not be able to assign BT1 into BT2, and that will be flagged as an error, but on the other hand, we can assign BT2 into BT1 because that doesn't change BT2. It does change BT1, but BT1 is not a const. Finally, we're going to take a look at const with respect to pointers. First, on slide 19, we have an example we've seen before. If I write hello in double quotes, that is a string literal stored in the static data area. What I get from the compiler at the point where I wrote that string literal is the address of the little h at the beginning of that 6-character array, H, E, L, L, O, and null. Now that string literal in the static data area cannot be changed. Therefore, in order to save the address of the little h, I need to save that into a variable which is a pointer to a character constant. That means that p itself can change. P is just a pointer, but the thing that p is pointing to cannot change. All right? If I say cout insert of star p++, since this is a post increment, it modifies the pointer p, but only after the value of p, that is the address of the little h, has been used. So what this statement does is to display the little h and then bump the pointer ahead to point to the little e. Now I'll display the little e, and that will work just fine. But if I then attempt to say star p gets a little u, that would be an attempt to replace the little e with a u. That's going to be an error because I cannot modify a character constant. Saying star p gets little u is an attempt to modify indirectly a character constant. Now on slide 20, a here is being declared as an array of char. The array a is being initialized from the string literal hello. That means that a is going to be an array of 6 char, H, E, L, L, O, and null. And the array a is variable. That is, we can change any of the 6 chars that are contained within this array a. In this case, P, notice how careful I am to read this from right to left. It looks sort of similar to what we did on the previous slide, but this says that P is a constant pointer to a char. That means that P itself is a constant. It's a constant that points to a char. The char that it's pointing to is not constant. P is initialized with A. Since P is a const, it has to be initialized with something. All right, P is a constant pointer to a char. P is initialized with A, that is, P points at A sub 0. If I say star P gets J, that's fine. That's going to replace the little h, the first character within the array A, with a J. So now the array A contains Jello. I did not change P there, I changed the thing that P was pointing to. If I attempt to change P, however, if I say plus plus P, or P plus gets 1, or something along those lines, that will be flagged as an error because P is const. Okay? So on 19, P is a pointer to a char, which is const. On slide 20, P is a const, which is pointing to a char. And of course, we can have const in both locations. P in slide 21 here is declared as a constant pointer to a character constant. That means that P can't be changed because P is const. It also means that the character that P is pointing to cannot be changed because that character is also const. I can access P. Here P is pointing at the little h in hello. So displaying P to see out displays hello. I can also access one of the elements within the array that P is pointing to. P sub 4 is going to be the sub 4 element of hello. So that's fine. But I cannot change the thing that P points to because P is pointing to a character which is constant. And I also cannot change P because P itself is a const. All right, and finally here on slide 22 and 23, here we have a class employee that has a data member which is const. ID is an int const. A const has to be initialized. How do we go about initializing this const data member of the employee class? Well, we do that in the constructor, and in this case we must use the member initialization list to initialize ID. If we decided that we didn't like that notation and instead we would rather say ID gets I in the body, that's going to fail because ID is a const. All right, so a const must always be initialized. If a const is a member of a class, that means it must be initialized in the initializer list. It can't be initialized by assignment later in the body of the constructor. Okay, so that takes care of typedef and const.